So my name is Mehdi Azani, and I'm here today to present mmFormer multimodal medical transformer for incomplete multimodal learning of brain tumor segmentation. This paper is from UCLA University and the Lenovo company in China. So it was published in MACAI in 2020, MICCAI in 2022, and it's a pretty interesting paper, so I will go through it at once. So the motivation of this paper is that they want to accurately segment the brain tumor from MRI images. So the MRI images have multimodal images that consist of different details. So it is not always possible to acquire all complete set of MRI. For example, a patient can move, or the facility that they are doing the MRI can have a cropped data or something else. So it's not always possible to have all the models of the models of the MRI. And the problem of missing modalities cause severe performance degradation in existing models. So they set to mitigate this problem and create a new framework. So the problem statement for this paper is that how to accurately segment multimodal brain tumor MRI images robust to missing modalities. So that's the problem statement that they are proposing here. So the main contribution that the authors say in this paper is that they are first model to attempt to exploit the transformers for multimodal brain tumor segmentation, which is robust to any combination of subsets of available modalities. So I'm going to the introduction. So MRI have different modalities. And as you see here, there are three different modalities in here: T1 weighted, T2 weighted, and flare. As you see, there are different details available in each of these modalities of MRI. So if I want to summarize it in the table, there's as you see, there are differences between the modalities. For example, the white matter in T1 weighted is light, and the T2 weighted is dark gray, and phrase dark gray as well. So it's different between each modalities, and the details are different. For example, here in the T1 weighted with GAD, you can see the bright signal in blood vessels, but in T1 weighted you cannot see them. And here, for example, in flare, you cannot see the infection, and in diffusion weighted, you can see the infection right here. So it's pretty obvious that if you have multiple models, you can, as a human, at least you can actually classify them better. But they are set to reduce this dependability of model on different models of the MRI. So for the related work, they mentioned fusing multimodal MRIs for brain tumor segmentation have they mentioned two general methods that are concatenating multimodal images in channels dimension as the input. So they stack them together as channels, and then they pass it to the model, and this is the example of this work. And the second one is fusing features in the latent space. So they extract the latent features from each model, and then they can fuse it in the latent space. And this is the example for the second approach. For the incomplete multimodal learning, they also call it heteromodal learning. They can have different approaches as well. So synthesizing the missing modalities by generative models can be one method to make the framework robust to missing modalities or knowledge distillation from complete modalities to incomplete ones. So these are also the different examples of these works. Although promising results are obtained with these two approaches, some such methods have to train and deploy as a specific model for each subset of the missing modalities. So which is these two approaches are very complicated and burdensome, including applications. So another thing is that assembling learning of single model models with adaptive fusion to achieve multimodal segmentation. This is another approach to the robustness and modality-aware natural learning for multimodal medical image segmentation is the only work available that it only works that when one of all modalities are available. So they mention two works in this area. Learning a unified model instead of a bunch of distilled networks for incomplete multimodal segmentation, which is these two works that they are comparing their model against in the results. So let's move forward. So they are using transformers for this framework, which is a sequence to sequence task. They it started with the application in NLP, and after that they the people in the computer vision area adopted it, and it's has very different applications in various computer vision tasks, and brain tumor segmentation for from the view of the backbone network can be done and has been done before this work. So the method, if I want to go to the method, I need to break the method down into 4 modules. So it's a hybrid modality, a specific encoder for each modality. So the first one is a convolutional encoder. They have a convolutional encoder to generate a compact feature map with a local context, because as you know, the convolutional models have inductive biases, and they look through a local window of image, so they can aggregate the local features very well. And they use intramodal transformers in their hybrid approach of modality-specific encoder to get the long-range dependencies in the global space. So there are 2 parts in their encoder, each modality encoder. So for the convolutional encoder, they use the same architecture as the encoder of the unit. So they, as you see, they formulate it like this: the f of convolution xm, and this is the weight of the convolution. And they, as you see here, they use convolutional blocks to encode the image and get the locality features. So there are 5-stage encoders in the convolutional encoder. Each stage consists of 2 convolutional blocks. Each block has a group normalization, ReLU, and a convolutional layer with kernel size of 3. The first convolutional block has only one convolutional layer without any of ReLU and group normalization. Between 2 consecutive layers, there is also a convolutional layer with a stride of 2 to downsample the feature map, and number of filters for at each level of this 5-stage encoder is 16, 32, 64, 128, and 256. So for the intramodal transformers, they use the exact same architecture as Vision Transformer. So Vision Transformer encoder, as you see, there's a patch embedding, and there's a layer normalization, multi-headed attention, and with the skip connection, and then normalization again, and multi-layer perceptron. So tokenizer, multi-head self-attention, and feed-forward neural network, which is this NLP. For this, they use exactly the same architecture. It's nothing novel in this architecture for they didn't change anything in this architecture. So they also mentioned that they use positional embedding as well, exactly the same way as the vision transformer paper in 2021, and they use the key query values linear projections of key query values for the self-attention, and then they use self-attention mechanism to extract the embeddings of the tokens. So as you see here, the f of global, which is the output of the intramodal transformers, is formulated like this. So if we want to aggregate these two parts, we get to something like this. We get two convolutional encoders for each modalities, and then we linear project them to get the tokens, and we use positional embedding to give the transformer context of the position of each token, and then we use the self-attention, and we get the embeddings of each model after that. So we can go to the next part of the framework. This next part of the framework is modality correlated encoder. So they call it intermodal transformer. After they get the encodings of each model, they use Bernoulli distribution of zero Bernoulli like Bernoulli the distribution for them to can on or off each one of the modalities here. So they can, for example, have the flare or not have the flare. They can have the T1 or weighted or not T1 weighted. So that's the thing that they are doing to make it robust to the and because the transformers are not restricted to the number of the tokens that they have, they can do this because they can have some token, and for example, they can have 12 token in one run and have 20 token in another run. So it's possible to do this in this way. So after they extract the embeddings from each model, they can use the self-attention again to get the connection between the modalities as well. So as you see here, after they get the embeddings, they come here and they multiply it with the Bernoulli. Go on, sorry. Okay, so they multiply it with Bernoulli indicator, and they get the second tokens, and then they use the self-attention mechanism to get the connection between the tokens. So they have another part in their architecture that is convolutional decoder to get the map of segmentation. So they progressively restore the spatial resolution from higher level latent space to original mask space. The F global that we got from the intertransformer is reshaped into the feature maps corresponding to the size before flattening, and the skip connections are between encoder and decoder are also added to keep more low-level details for better segmentation. So it's this comes from exactly comes from the ResNet with the residual connections. So they have another part in their framework named auxiliary regularization, which is the convolutional multimodal learning models tend to recognize brain tumors relying on the discriminative modality. So that means that if you are depending on one modality to predict whether or not there is a tumor or segment the tumor in the MRI image, you cannot be robust to the modalities, right? So they want to be robust to the missing modalities. So if we have this kind of thing, the model face severe degradation and the discriminative modalities are missing. The outputs of convolutional encoders are upsampled by the share weight decoder in the auxiliary regularizer, and by share weight decoder to segment tumor for each modality separately. So the shared weight decoder has the same architecture with the convolutional decoder in the unit that I mentioned before, and the auxiliary regularizer in the convolutional decoder is there to force the decoder to generate accurate segmentation even when the certain modalities are missing. So as you see, there's the first part of the framework, which we get this auxiliary regularizer from, they are upsampling inputs from the convolutional layers, convolutional encoders, and the upsampling from the convolutional decoder, and we get the reshaped map of the tokens that we have from inter transformers to get the final segmentation map. So they use three loss function. Different loss function, different part of loss function. They use the dice loss function for the auxiliary regularizer. They use the loss of the encoder, so and they have the loss of the decoder. So the loss of total is the summation of these three terms. And if I want to quickly say what's the dice coefficient, is actually the overlapping between two set of data, and it's giving the information about the overlapping between the two set of data. So it's been in work in computer science, computer vision applications at 2016 for getting the segmentation. So it showed a better results than binary cross entropy for the image segmentation. So in the boundary detection task that the dice loss function is used, the ground truth boundary pixels and the predicted boundary pixels can be viewed as two sets by leveraging dice loss. The two sets are trained to overlap little by little. So as you see in this figure, the denominator considers the total number of boundary pixels at the global scale, while the numerator considers the overlapping between the two sets at local scale. So dice loss function considers the loss information both locally and globally, which yields better results in training. So if I want to aggregate all the framework, and we can see the whole framework here. We have the multiple modalities. We use the convolutional encoders, and then we use the transformers to encode them. Then we use the modality correlated encoder to get the connection between the different modalities, and then we use the convolutional decoder to get the segmentation. Also, the auxiliary regularization is used to make the framework robust to missing modalities. So for the result, they mentioned that they used the BRATS 2018 dataset for brain tumor. There is 285 multi-contrast MRI scans with four modalities, T1, T1C, T2, and FLAIR. Different subgroups of brain tumors are combined into three nested subregions: whole tumor, tumor core, and enhanced tumor. The framework is implemented with PyTorch 1.7 with 4 NVIDIA Tesla V100 GPUs. So the input size is 128 by 128 and 128 with batch size of 1. They used random flip crop and intensity shift for the data augmentations. The mmFormer has 106 million parameters, and 748 gigaflops. The network is trained with Adam optimizer with initial learning rates of 0.0002 for 1000 epochs. So if we want to see the segmentation results, there's the flare image, there's a ground truth. If we have all the modalities, as you can see, it's very similar to the ground truth. And in each image, we eliminate one of the modalities. And as you see, it's not very affected with the loss of the modalities. But as you see, in each part, it will lose a small detail. So their performance of the multimodal segmentation, they use the dice similarity coefficient for comparing them. As you see here, for the three subgroup that I mentioned, that they separate the data set to, with different combination of the modalities, as you see, there's improvement in all of them in comparison to the two other methods that are robust to the multimodal missing modal images. So for the ablation study, they actually did a very good job in ablation study. They actually did test their model with different part of their framework to see which part of the framework is most important, and the effect of each part, to see the effect of each part of the network. So the conclusion of this paper, I think the advantage of this paper is that the framework is robust to missing modalities of MRI. So it's very important to see that. And also the framework reaches a state-of-the-art results when all modalities is available, also available. So it's not only robust to the missing modalities, it's also better when all modalities are available. The authors examine different parts of their framework in aberration study, so I really appreciated that. And as I mentioned, it is really good to see such a study in their paper. So for the disadvantages, the authors did not test the importance of dice loss. So they just mentioned the dice loss in the end part of their methodology, and didn't expand on it, and didn't justify why they use dice loss. So as you see in the recent transformer papers, binary crossing entropy has proven to have yielded better results in pre-training, but they didn't use that in their method. Also, authors did not use transformer pre-trained backbones to boost the accuracy. For example, I think they might have used different transformer backbones to transfer, learn, and boost the accuracy, in my opinion. And they didn't even use, for example, different kind of transformers, because, for example, we have swing transformers, or they used vanilla transformers for their approach, and they didn't mention them in their paper. The author compared their results with only two other methods, so we cannot see if we don't care about the missing modalities. Is there a better or worse? Is there a better method in the literature that is that the authors can compare it to, and the high number of parameters and complexity compared to other models. So they have a higher number of parameters in their framework compared to the other two. So it's not a very fair comparison to see to say, okay, we have this model with 100 million parameters and compare it to a model with 20 million parameters. So for the future works, I think if we can use backbone to transfer learn the convolutional encoder and the intramodal modal transformers, it could potentially boost the performance of the framework, and we can use different regularization to improve robustness. For example, we can instead of the auxiliary regularizer that they have in their framework, we can have uh, randomly in each step we can have have it randomly enable or disable the uh, modalities that we have on the each MRI image. So thank you for your attention.